Oh, it's waiting. Oh, okay. It's good now. I don't know. The website just takes a while.
Yeah, we're good.
Okay.
Hello.
Wait, hold on. Is there echo? Can you say something? Hello?
I think it's fine.
Okay. All right, let's wait a little bit and we'll start. All right. Hello, everyone. Welcome to today's episode of Corecast. I am your host, Tim.
And I'm Mikey.
And this is Sahil. Welcome everybody to a brand new exciting episode of Queercast. Before we get started, if you haven't already, do join our Discord channel. And if you're watching this on YouTube, where we're trying our best to do this every Tuesday at 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions there, and we can get to them during the episode. Without further ado, let's get to it. So Tim and Mikey, we've been talking a lot about various problems in physics, and we've been talking in previous episodes about like all the different conundrums. And one of the biggest ones is this thing called dark matter. That is, that has been, at least from my perspective, has been quite a mystery for a while. So before we dig deep into like, I guess like where it is right now and what the problem is, can we discuss like what is dark matter? So one of you, I will actually, you know what, Mikey, I'm gonna put you on the spot.
Right. So, I don't know, as some viewers may have heard about, I mean, I guess the word dark matter gets thrown around a lot, like maybe in sci-fi movies or whatever. But right. So how to introduce this?
I mean, we can perhaps start
I think the first thing
historically.
to understand about
Yeah.
dark matter, sorry.
I mean, there's a historical lesson, but then we have a lot more understanding now. But go ahead, Mikey.
Oh yeah, yeah. I mean, but just to like start at the very, very basics of what dark matter is, I think it's important to understand that like everything that we observe in the universe, we observe through light, right? Like our eyes are sensitive to light, um, and all of the atoms in our body interact very strongly with light. So, you know, the bond that keeps the atoms bound together, the bond that keeps molecules, atoms together in molecules, the bonds that keep molecules together into like larger structures, everything that we use to interact with the universe is basically mediated by light. But when we look at the universe, if we assume that this light interacting stuff is the only stuff out there, you run into like a lot of problems, a lot of inconsistencies. And so there's a belief in the physics community that there's a bunch of stuff out there that doesn't interact with light. It's basically invisible to us. And I don't mean just invisible like to our eyes, like we can't see it, right? If there's stuff out there that is insensitive to light, it would literally pass through your bodies like a ghost. Like there's, the only reason why when I touch the table, the only reason why my hand doesn't go through the table is because particles of light are mediating an electromagnetic force, which is repelling my hand from the table. If there was some substance that was dark, meaning like it doesn't interact with light, then that stuff would literally be what's a better word than invisible? It would literally be like non-existent to us. It would literally just pass through us with no resistance. So physicists believe that there's a lot of stuff out there in the universe that is dark. It doesn't interact with light. And so that makes it inherently mysterious to us because we have no way of really detecting it. We have no way of really observing it. And so that's what dark matter is.
Can you give examples of like I mean, what discrepancies do you see? Like I don't see any discrepancies like where I am. I mean, like when I learned from, classical mechanics in high school, I didn't need like to introduce this like matter that doesn't interact with light to understand it. So what are we talking about here? What discrepancies arise?
Right. So like so there's basically only two forces that kind of determine like our everyday experience. One is like light, which I just mentioned, the electromagnetic force, and the other is gravity. Um, but when you look at the universe and the way like planets move around suns, the way stars move around in galaxies, um, when you look at the way like gravitationally interacting bodies move, it looks as though there's some invisible stuff there. I guess the most famous example is like when you look at the rotation of galaxies, right? Galaxies are a collection of stars that are spinning around,
Mhm.
and they're held together under the force of gravity. But when you look at them really closely and you study their shapes, you realize that there's not enough stuff there to really hold the galaxies together. If the stars and the dust was the only stuff that was there literally wouldn't be enough gravity to hold the galaxies together. They would fly apart. So one of the reasons why we think there's dark matter out there is because we observe these galaxies actually staying together in one piece, and that, according to the laws of gravity, that shouldn't be possible if there's only
Uh,
light matter.
that makes sense. Tim, one question for you is if this dark matter stuff didn't exist, and let's suppose galaxies could hold together, even though Mike, you just said they wouldn't. Would they be like disc shaped, or would they be like kind of this like I don't know, like spherically shaped that we see?
Yeah, actually, there's an issue with gravity. Is that oh sorry, there's an issue with conventional interactions in everyday matter, the
Hmm.
electromagnetic interaction. The problem is that it's dissipative. Basically, basically, if for example, if I hit my hand together, you kind of feel friction, you kind of feel heat coming out. Some energy is lost. And that generalizes to celestial bodies, right? Like if a sun collide with another, if a star collide with another star, some energy gets lost. And at the grand structure of things, if the entire galaxy is made of these dissipative stuff, eventually the galaxy become very unstable. It will collapse, and it just really it doesn't even make sense to talk about the shape of the galaxy. Like it just wouldn't hold. Also, the disk is incredibly thin. If you look at the profile of typical galaxies, the thickness of it versus the size, it's incredibly small. And you can kind of imagine in a galaxy that's millions of light year across, like one end of the galaxy does not know about the other end, right? Because it takes light that long to travel, and as a result, without something like some kind of a gel, I don't know what you call it, some permeating stuff to kind of hold it together, all the spiral arm, the shape would just become increasingly wobbly and just completely fall apart, like what Mikey's saying. And yeah, it doesn't even make sense to talk about galaxy without some extra structure to hold it in place.
Hmm. I guess one thing I want to touch on just for maybe like a minute or so, I don't want to spend too much longer in here, is what about the possibility if you had like, say the laws of gravity are like, the way they are on Earth, but as you start to get to larger scales, they change. Is that a possibility in your mind, or what would you say to people who subscribe to that notion of like a
I mean,
so-called modified gravity?
yeah, I mean, clearly that's a plausibility. But keep in mind that this absence of extra stuff, um, it's actually a lot more prevalent than people thought. It's not just that when the universe is large, we observe these differences. So the
Mhm.
thing that Mikey was saying, oh, how it affects galaxies, that's just one small aspect of the mystery of dark matter. And also, remember, the universe in the beginning used to be very, very small, right?
Mhm.
The universe in the beginning was just a small hot plasma. And at that point, you can't say the same thing that gravity is somehow different because the thing was small, right? But we still see the effects of dark matter early on because so what happens is in this plasma fluid there could be waves like water waves. In the ocean there are water waves that moves around, and in these plasma fluid there are sound waves as well, kind of like ocean waves that are moving around. And these waves, what they create is slightly hotter and slightly colder spots. And as we know, as the universe expands, all that plasma is the seed to galaxies and everything that surrounds us. And it turns out that because of dark matter, there's a little bit more, but not too much, just like a Goldilocks amount of extra sound wave, density waves, in such a way that it shapes the entire structure of our universe. So we see, and this has been recent, I think. It goes under the name, I don't want to be technical, but there's a technical name. It's called baryon acoustic oscillation, but never mind that. But basically, it's that when people look out in the galaxies, they see like patterns of galaxies in the sky. It matches what the early universe, the plasma, looks like, and that influences not just individual galaxies, but like the entire universe itself. So, and that's just one other evidence for dark matter, and there's also a few other more. I don't think we have time to go into every single one of them, but just to emphasize, like, this will require modification of gravity, not just when things are far apart, but also when things are nearby. It requires, if Einstein was wrong, it will require complete overhaul in some really intricate way, and nobody has come up with an answer to that yet.
Nobody. Yeah, I mean, so just to follow up on that, yeah, like it's a natural question to ask, right? Like, so like what I said before was like when you look at gravitationally interacting bodies, it looks like there's some extra stuff there. So yeah, it makes sense to ask, oh, what if your idea of gravity is just wrong? What if it's just approximate? What if there's some corrections to gravity that explain this? But as Tim mentioned, it's not just the rotations of galaxies. Like people actually write very detailed computer simulations of the Big Bang. And when you look out in the universe, you see a very specific pattern of how stars and galaxies and planets are all arranged. And these computer simulations, they start from a Big Bang and they just play the tape forward. And it turns out that if you want to reproduce what we see in terms of these patterns of galaxies and stars and stuff, you have to put in something like dark matter into these simulations. If you don't, you get something that looks nothing like our universe. But if you do just assume that there's some invisible stuff out there and you add that to the computer simulations, it looks exactly like our universe. So that's just like one of the extra pieces of evidence. And as Tim mentioned, there's so many things that would be like, if you assume that maybe your idea of gravity is wrong and you have maybe there's like this correction to gravity. It's extremely hard to get that to work out in simulations of our universe. It's just very obvious that there's some stuff out there that we can't see.
Interesting. So what you're saying, both of you, what both of you are saying is that it's not just like these rotation curves or how stuff is moving within a galaxy, but it's even the greater structure of the universe itself really depends theoretically on this stuff to exist in it in order to make sense, at least based on current theories.
So far, that's what it seems like. And also, like, it's a very simple explanation, right? Like, it's kind of arrogant to assume that the entire contents of the universe would be visible and observable to us. It's very easy to imagine that there could be particles or substances out there that, just don't interact with light. And it's a very simple, that's all you need to explain what we see. And every single person that has tried to explain this by changing gravity or by assuming that Einstein was wrong or something like that, like, okay, you might explain this, but then it comes into great conflict with other observations. And it ends up being like a very tricky game.
Gotcha. Before we jump to maybe some details on potential experiments or also experiments that were designed to try to, observe dark matter, what if we kind of ask the converse question that, like, what if dark matter could interact with light and it was there? Like, what would the universe look like? Would life actually even exist if dark matter could interact with light?
So
interesting. Wait, so like, what if like, let's say that like there was just a lot more like, no, yeah,
that can't possibly work. So okay, if it interacts with a very, very tiny amount with light, but very different from ordinary matter, then it's okay. But if dark matter has similar interaction with ordinary matter, it's still the whole galaxies would just collapse. It wouldn't be stable at all.
Because of the friction, right?
Sorry?
Because of the friction, right?
Exactly, and this is exactly what I alluded to earlier. The problem with ordinary matter is that it's dissipative. If dark matter itself is also dissipative, that means the scaffolding function dark matter provides to galaxies and the entire universe, it will collapse. Like the scaffolding will just dissipate itself, and galaxies will likely collapse into black holes and all that. I mean, there could be a multiverse out there where a universe looks like that, but that's certainly not the universe that we live in. So I would say, by that definition, dark matter definitely does not interact with light, at least not the way that we think of in terms of dark matter interacting with light.
Oh, can I also mention one thing about, like, as far as we're talking about, like, evidence for dark matter? Like, we've actually kind of observed it in some sense. So, okay, I guess, so, gravity actually bends light, right? Like, particles of light, when they travel through the universe, they're actually influenced by the force of gravity. So if you have a very massive body and there's some light shining behind that massive body, you actually see the light curving around that body under the force of gravity. And there's actually, I don't know when it was discovered, when do you know when the bullet cluster was discovered?
Yeah, I don't remember.
90s, maybe?
19 something, yeah.
Something, yeah. But anyways, like, so, I guess, I don't know, maybe I'm wrong about this, but sometime in the 80s or 90s, people observed like a very interesting kind of galaxy where two galaxies collided. And because the light matter is it strongly interacting with itself, the two galaxies actually kind of clustered together after they collided, but something passed through. And you can actually see the light bending around something that appears to be totally invisible. And this colliding galaxy system was originally called the bullet cluster. And that, to me, I think was like the most like inescapable evidence for the fact that this dark matter actually exists. Because you actually see the dark matter separating out from the galaxy, and you see the light bending around this somehow invisible stuff. And since then, we've found, dozens and dozens and dozens of more examples of galaxies like this, where you can actually literally see the dark matter, and it looks like there's literally nothing there, but somehow there's something making the light bend around it under the force of gravity. So to me, that just makes it like, undeniable that there's some invisible stuff in the universe, and it makes up a significant part of our universe.
Very, very fascinating. So you talk about light bending for our audience members. That means, like, if I have let's say I had a very massive object in front of me, or some distance away in front of me, and light bends around, that means I'd be able to see what's behind the object. Some sense, see what's behind it.
Yeah,
Right?
yeah, exactly. Yeah. Like, an object that would normally be invisible to you because it's being blocked by an object, the light from it actually bends around so you can see it. It's actually called gravitational lensing because it kind of bends light the way a lens does. And if you've ever seen like the movie Interstellar, or like seen pictures of black holes, they always have this effect where you can kind of see the light bending around the object. And yeah, it looks like a little weird disk, but yeah. But we've observed this happening with dark matter in a very, like, I don't know, tangible sense.
Gotcha. So, why don't we jump to experiments? Like, how do people even think about like designing experiments for this? And like, actually, one thing kind of make this down to earth. Is there a very real possibility that like dark matter is right here, right now, like in your room, Mikey, like just
Yeah,
passing through you?
yeah.
Okay.
You can calculate the amount of it.
Yeah, but I think it's not very much. I think in the entire Earth, it's about, is it a kilogram or gram? Because remember, dark matter is very, very diffuse. Because dark matter is not dissipative. In order for things like planets and suns to form, you need something dissipative so that it clumps. But dark matter, even though there's so much of it in the universe, and just to throw some numbers around, the amount of visible stuff we see in the universe is about 5% of the entire universe energy budget. Dark matter is about 20%, and the rest is
25.
dark, something like that. Yeah, and the rest is dark energy, right? And going back to that point, yeah, dark matter is very diffuse, so there isn't that much of it on Earth, like in terms of grams or kilograms. But yeah, there could be some enough particles that passes through us right now, but it doesn't do anything to us.
There's definitely dark
Gotcha.
matter in your room right now. 100%.
So I guess like coming back to experiments, how have people tried to design experiments like fish this out, if at all?
I think the experiments are actually very reasonable. It's almost like a child is asking, hey, dark matter is dark. How do we test this, right? And the first and most natural thing is it really dark? Can dark matter emit light? So we have plenty of telescopes that looks into the sky to see locations where dark matter might be as dense as possible, like the center of the galaxy, to see if maybe occasionally dark matter can light up one way or another, either through maybe dark matter will hit something else, maybe dark matter can collide to itself and emit some kind of a light. So we try to observe that, and we also try to make it. We try to make it in the lab. Is it possible to make dark matter? We try to do it in collider experiments. And we also try to see if we can directly observe dark matter on Earth, because we mentioned that dark matter is passing through us, potentially every second. Well, maybe occasionally this dark matter will actually feel it. Of course, we don't use people, right? That we use instruments to see if they can feel this dark matter passing the instrument. So these very natural, three frontiers of experiments are very much under the way. And scientists are trying their darn hardest to try to find dark matter. Still ongoing.
I see.
They all
So
kind of depend on this idea that dark matter is not 100% dark. Like, suppose you have this substance that only interacts with light with a probability of like 1 in a billion, right? Well, there's so many particles in the universe. I mean, there's something like, if you take just like a cube, let's say you take a cube of material, there's so many particles in there. Even if dark matter only interacts with with light matter, like 1 in a billion. If you have a billion particles, you might see dark matter once in a while, maybe hitting the nucleus of an atom. So I guess like the most direct experiments that people do is they take like the densest material that they can find, where it has like, maximum number of like nuclei, maximum number of atoms, per square inch, and they just wait for a long time to see if maybe once in a while you get something that just kicks it that you can't explain. And maybe that's the dark matter.
what about any experiments that like indirectly test for dark matter through like gravity? Because gravity interacts with light, and we know dark matter interacts with gravity. So how difficult would that be to design an experiment here? Or like why can't we do that
I mean, we kind
if
of
we
do. I mean,
can?
so like we can observe, like with the bullet cluster, we kind of observe the gravitational effects of dark matter. But to
Mhm,
really be confident that you've kind of discovered it or explain, you have to do it. You have to make it in the laboratory, or you have to find
mhm,
some kind of evidence for it in the laboratory. And because the gravitational force is so weak, it's not
mhm.
impossible, but it takes a very, very clever setup to um, try to detect dark matter through these kinds of gravitational experiments in the laboratory.
Mhm. Gotcha. So that makes sense. So experiments. So if dark matter is truly 100% dark, does not interact with light, then none of these experiments would work.
Then there's no hope. We'll never see it. It's
I
scary.
see. I see. Uh, that makes sense. I guess then, why don't we talk about like candidates for dark matter? Like theoretically, like what are people thinking they look like? And then there's an audience question pertaining to that. But I want to set the stage first of discussing like historically what's come up.
Yeah.
Uh,
yeah, I think given the state of particle physics experiments, there are generally two very natural camps of what dark matter is. I think the first camp is the massive particle paradigm, and it's very old. And the idea is that, first you have to reconcile a few facts, right? So first of all, dark matter is very dark, and we have not seen it in the lab. You know that in the lab we collide particles to create new particles. So it's not hard, if dark matter does exist with some large enough interactions, we might just produce them in the lab, right? So you have to reconcile with the fact that, well, how the heck have we not produced them in the lab yet? One very plausible explanation is just that, well, maybe dark matter is just really, really heavy, because when you collide something, you need to put in enough energy to produce something heavy, right? So if dark matter is so heavy enough that it's plausible that maybe we just have not produced this kind of matter in the lab yet. And also, it turns out coincidentally, if you have matter with that kind of masses, and then it turns out that there's a lot of theoretical models that predicts particles with similar properties that are stable, that are very massive, that interacts very little with ordinary matter. So then these coincidences kind of melt together, and we're left with a paradigm that, hey, maybe there's new physics that we're missing in such a way that there actually exists a massive particle, massive enough that we haven't produced, and it's stable, and it was created when the universe was young, and that just becomes dark matter. So that's the I would say probably the leading paradigm of dark matter currently, right?
Used to be, maybe. No, I mean, like as Tim said, it's actually like very, very natural. So like people might, it's not that widely known, but there's actually a particle that we know about called the neutrino, and it behaves very similarly to this dark matter particle. And we've seen this particle in the lab. It basically is almost totally neutral to light. It's neutral electromagnetically. It doesn't interact with light almost at all. It does a little bit, but I don't know how many neutrinos are passing through our bodies every single second. We don't even notice it because it doesn't interact with light. And there's a lot of theories. Like anytime you write down like some kind of theory of nature, it's very easy that this theory just accidentally produces some neutral particle. And those neutral particles play perfectly the role of dark matter. And so that's one of the reasons why, as Tim mentioned, this kind of paradigm that there's this heavy particle that's just neutral. And that would explain everything we see. And it's very easy to imagine that such a particle could exist. And yeah, that's been the paradigm for a while.
So, Mike, you seem to be alluding to that a new paradigm is there. If I understand your change in your voice.
Yeah, I mean, not. So basically, I guess like to air out the dirty laundry, like every single attempt to try to find some kind of heavy neutral particle that maybe is like a neutrino, maybe it interacts with light a little bit, but it's just a little bit heavier than a neutrino, and it's all failed. Like people have been running experiments for like 10, 20 years. They've been setting up boxes of dense materials, waiting for something to hit, and just nothing's come up. But yeah, it turns out that there's actually recently like kind of more popular theory that's gained a little bit more attention, that maybe dark matter is just so light. It's just so light, and there's so many of them that they kind of form like this like cohesive fluid. I feel like I'm not explaining this.
Yeah, well, let me add that, people might ask the question, why do we care whether it's heavy or light? What difference does it make? Well, keep in mind that the only evidence we have for dark matter is its gravitational influence. So we don't know the mass of the individual particle that could potentially make up dark matter. So we only know the total gravitational influence. And as you know, gravity depends on mass, right? So if the mass is really heavy per individual dark matter particle, then that means there could be less dark matter, right? But the same, so that it still has the same total gravitational influence. But if the mass of the dark matter is much lighter, then there will be a lot more dark matter, so that the total gravitational influence remains the same, right? And in the beginning, people didn't like kind of the light dark matter paradigm, is because if you have such light dark matter, there will be lots of it. Then then there's very good reason that maybe we should have seen it. Why is it so hard to find? And also, when dark matter becomes very light, when it's like a soup, it tends to have the possibility for it to kind of warm up, I guess, and that kind of messes up the structure of the universe. Remember, for it to be a scaffold, it needs to be like a sturdy scaffold. If a dark matter is light, and if it's warm, by warm I mean it moves around a lot, because things that are light are easily accelerated and moves around usually at a higher speed, right? Yeah, then this scaffold will kind of screw up the universe. Like, we want something sturdy and heavy, kind of forms to, help galaxies form, right? So we don't generally like things that are very light. So historically, that's the reason why we don't like light dark matter. But as Mikey was saying, decades of experiment, and these experiments are very, very tuned, I think, to the massive dark matter paradigm, right? The experiments are generally better if dark matter was heavy, that it has a better chance to detect them. So they neglected the possibility that dark matter could be light, right? But in recent years, yeah, the fact that we haven't seen anything, then people are like thinking, maybe we haven't covered all our grounds. Maybe nature is a little trickier than we expected. So that's why, the light dark matter paradigm has kind of gained more traction as opposed to the conventional one.
Then that begs the question, Tim, as you mentioned earlier, like, why don't we see it in accelerators and stuff like that if it's so light? What's kind of the potential answers for that?
The potential answer is simple. The reason we haven't seen them is just the interaction is just so darn small. Even though they're so light, they're so easy to make. If the chance of making them is so low, it's like winning a lottery multiple times in a row. If the interaction area is so small, then maybe we just haven't seen it yet. But in generally in particle physics, people generally don't like very small numbers, because you're like, well, why are these numbers so small? Like, it's like winning a lottery. We don't expect lotteries to be in nature, but it could be true, right? So yeah, to go back to your question. The answer really could just be that it's just small. It just happens to be hard to make them. That's pretty much the answer.
Gotcha. That makes sense. So I think this is a nice segue into an audience question that was asked. Either one of you can take this. And I apologize if I'm mispronouncing the two people's names in here. Do you have any opinions about the progress of Eric Verlinde's work and Lee Smolin's work on dark matter, that it doesn't exist and it's actually emergent phenomenon of dark energy and modified GR?
Eric Verlinde, yeah.
I guess before answering that question, can we break down what is the question actually asking, just so the rest of the audience understands?
Yeah.
So Eric Verlinde had this theory, like 5 to 10 years ago. It was based in string theory. Gosh, I can't exactly remember the details of it right now.
The theory is very vague. Let me just tell you. The theory is very vague. It doesn't say very much, but it says that if there's some unknown stuff in the theory, gravity could be emergent in some ways. So these, at least in Eric Verlinde's theory, he's not just modifying the equations to fix dark matter. He's completely throwing Einstein's theory to the trash, right? Like, it's a complete overhaul.
Not really.
Okay, but maybe I'm being a little too dramatic. But in any case, maybe his equation explains dark matter, but even that's vague, right? His solution was very vague. But let me just say, it does not explain the structure of the universe because in the public press, there's too much emphasis on how galaxies rotate. That's just one piece, one out of bazillions of pieces of evidence for dark matter. Maybe his theory can help explain how galaxies rotate, but remember, when the universe was young, there were no galaxies. We still see dark matter in the sound waves of the plasma. So theories like the ones Eric Berlinde proposes has nothing about that. It does not explain the baryon acoustic oscillation. It doesn't explain the large-scale structure of the universe, how things are clumpy, but not too clumpy. You need the right Goldilocks amount of dark matter. Like Mikey was saying, it doesn't explain how you run simulation with dark matter, you end up with the universe, right? So it pretty much, it may be some of them. I'm not familiar with the other person's work. So many of these theories kind of gain the public, I don't know, somehow they gain a lot of press because they taught it themselves as some kind of paradigm changing new theories, but not really. It's missing a lot of pieces, and ultimately these aren't very good theories because it failed to explain a few key parts about our universe.
I'll be a little more forgiving. I just remember, so Eric Berlinde, he had this theory of like emergent gravity, right? And I forget exactly how that's related to his dark matter theory, but he gave a talk at the Jerusalem IS where he calculated, like, so in his paradigm, it relates to string theory too, and in his theory, like the dark matter are certain modes of vibrations, and visible matter are other modes of vibrations. And he actually got the 25% to 5%, 25% dark matter, 5% visible matter. And I remember David Gross was like really impressed with that. He was asking a lot of questions. I think it's like a creative attempt to address this problem from a different perspective. But I think the key issue with that, as Tim mentioned, is that there's just so many different places where there's evidence for dark matter. And yeah, his theory couldn't explain like the early universe cosmology. It couldn't explain the baryonic acoustic oscillations, and those are the natural questions that people asked during that talk. It's a nice idea, and he got some, you know, some very interesting looking results from it. But the evidence for dark matter is so multifaceted. Like it just couldn't get every single thing right about it, which is a really tall order. But I don't know. I give him respect for trying. Lee Smolin, I wouldn't necessarily trust much of what he says, but I don't know.
Yeah, I would say some of these work. I mean, not to discourage scientists going out of the way. These might be like 0.1% of the final answer, right? Like they might capture some essence of what dark matter is that the conventional theory are not able to capture. It's plausible, quite plausible, in fact, because we still don't know what dark matter is. Maybe dark matter has these special properties that could make it appear, to conform to the equations of some of the physicists that proposes, right? But I think it's dangerous to take those theories too literally. I think every paper on dark matter should be taken kind of with a grain of salt. Like maybe it captures a little bit of truth, but certainly not even close to a significant portion of the whole truth.
Yeah, I think the problem is that cosmology has grown into such a precise and such a well-founded field of study, and there's so many measurements from so many different directions, and they all kind of point towards the same thing. So if you have a theory of dark matter that's outside of, whatever the normal paradigm, it's a very tall order to satisfy all of these experimental constraints that we now have.
That absolutely makes sense. Yeah. So we're almost at time. I want to give you guys the chance to leave the audience with any final parting words about dark matter.
Well, I think for me, like, dark matter is one of the, like, it's one of the biggest mysteries, one of the biggest unsolved mysteries in physics right now. And the scariest possibility to me is that, what if it's just completely dark, as we discussed before? Like, what if it doesn't interact with the light at all? That would be perfectly consistent with everything that we know, and it just means that we'll probably never know the truth about it. But you can't make progress by thinking that way. So people try to make progress where they can.
Yeah, and I guess I'll go back to maybe our previous episode on, what does the next particle physics breakthrough looks like. And the story of dark matter, I think, is a perfect example. There's some missing stuff, missing interaction in the universe. And I think generically, what that missing stuff is, we can quantify it as a particle. And even if you subscribe to modification of the Einstein theory, you can separate that modification, and it probably has to satisfy a bunch of other criterion to conform to what we know about the universe. And at the end of the day, you're gonna get something like dark matter. I don't know, if you don't like the word dark matter, call it something else, dark stuff, okay? But at the end, it's gonna be something like a new particle, right? Because as we mentioned before, the idea of particle is very generic. But like Mikey said, this is one of the puzzles that there's no guarantee. We could be one of the multiverse. Dark matter could just happen to be completely dark. And the nature of dark matter might not shed us any light about the nature of our world. It could just be literally an accident. But science continue to progress, like the Higgs boson, gravitational wave, those take 50 years for results to come in. I mean, the thing about dark matter is we don't know how long it's going to take. It could reveal us great truths, or it could be nothing more than just another new particle, and that's it. But in the spirit of science, we keep going, and I guess that's the beauty of it. We don't know what it is, but we keep trying to look for it.
Yeah, I hope on that note, I hope this episode shed some light and we didn't leave you guys in the dark about dark matter.
I see what you did
Pun.
there.
Yeah. It's a really, really bad pun. Anyway, yeah, so I want to thank everybody for joining us, and we'll see you all next week.
Yeah.
Bye.
Bye bye.